So in this example problem, we have a disk that has an outer radius of 6 inches, and then we have an inner radius of 1 inch, and inside that disk we have a shaft that has an outer radius equal to 1.003 inches. Okay? Both the shaft and the disk have the same material properties. They have an elastic modulus of 30 MPSI and 0.29 for the Poisson's ratio. And they both have the weight density of 0.284 pounds per inch. So we're asked to determine what would be the stress distribution at a rotational velocity of 5,000 RPM. Okay. So, so in order to calculate the stress distribution of the disk at 5,000 RPM, the first thing we're going to need to do is we need to find what will be the interference pressure at 5,000 RPM. Alright, so we want to find what will be the interference pressure at 5,000 RPM. So we know that interference pressure is a function of the interference between the inner and the outer cylinder. Okay, so the interference of the inner cylinder, or the radius of the inner cylinder, minus the inner radius of the outer cylinder is going to be our interference pressure. So the issue we have is we typically, if the shaft was not spinning, we could use the 1.03 and the 1.0 inches to solve for our interference. But since the shaft is spinning, our inner and our outer radiuses are actually going to be different due to the radial and tangential stresses that are caused during due to the rotational force or the rotational forces. So what we're going to do here is we need to figure out what the change in the radius of the shaft is, and we need to find what the change in radius of the disk is in order to find the delta at 5,000 RPM. Okay, so we know that the radius of the shaft is going to be equal to the radius divided by the Young's modulus times the tangential stress minus the Poisson's ratio times the radial stress. Okay, so alright, so what we can do here is we know that if we're only going to be considering our the stresses due to rotation at this time. So for a cylinder or a shaft that's undergoing a rotation and rotation only, sigma theta at R is equal to R out is equal to 0. Oh, sorry, sigma R. Sorry, not sigma theta. That's our boundary condition. Alright, so then we're interested in finding the displacement at R is equal to RO. So what this equation ends up getting is UR of our shaft will be equal to the outer radius of their shaft divided by E times sigma theta. Okay. So we know the outer radius, we know the elastic modulus, so we just need to solve for sigma theta. Okay? So we know that sigma theta is equal to our mass density times omega squared times divided by 8 times 3 plus the Poisson's ratio times the outer radius squared minus 1 plus 3 times the Poisson's ratio times the radius squared. All right. So this is for this is the equation for a shaft. So we can do here is we can plug in R is equal to R0. All right, and if we do that, we'll end up getting we plug in R is equal to R0, which was equal to 1.003 inches. We know what omega is going to be equal to 5,000 RP revolutions per minute times 1 revolution is equal to 2 pi radians times for 1 minute you get 60 seconds. So if we multiply that all out, we'll end up getting 524 or 523.6 radians per second. And then we need to find our density. Our density is going to be equal to our mass density, which was equal to 0.284 pounds force per inches cubed. Alright, and we're going to divide that by g, or 32.2 feet per second squared. And then we're going to multiply that by, to get everything in terms of inches, we're going to multiply that by 1 foot divided by 12 inches. Alright, and we'll end up getting pound force per second squared per inches to the fourth. Alright, and that'll be 7.35 times 10 to the minus 4. Okay, so if we plug in all those values into our equation here, we'll end up getting sigma theta is going to be equal to 36.0 psi. Not too bad. Alright, and our radius, or change in radius, u of r, is going to be equal to 1.20 times 10 to the negative 6th. If we plug in this term into our term here, alright, and we'll get, and we know that u of r is equal to the radius, outer radius at our velocity minus the radius at omega is equal to 0. Alright, so we end up getting r0 minus the initial dimension, which was 0.003 inches. So our new outer radius at 5,000 RPM is just going to be equal to 1.003 plus 1.2 times 10 to the minus 6, which is going to be equal to 0.012 inches. Okay, so basically the shaft does not really change at all. It's approximately the same thing. Alright, and now we can repeat this process, alright, for the disk. Okay, so we know that for the disk, we can use the inner at the inner radius of the disk. We know that u of r will be equal to r divided by e times sigma theta minus Poisson's ratio times sigma r. We can simplify this down to be just r divided by e times sigma theta, since sigma r is equal to 0 at the inner radius. We talked about this, the boundary condition for tangential, for radial stress in a rotating component. So we know r, we know e, we just need to solve for sigma theta. So if you solve for sigma theta for a radial disk, it's going to be equal to, this is equation 30. We get 3 plus the Poisson's ratio divided by 8 times omega times the rotary velocity, the rotational velocity squared, times, let's see here, times the inner radius squared plus the outer radius squared, plus the inner radius times the outer radius divided by the radius squared, minus 1 plus 3 times the Poisson's ratio divided by 3 plus the Poisson's ratio times the radius squared. Alright, so we're plugging this all in at the inner radius. So r is going to be set to be equal to ri, alright, which is going to be equal to 1.0 inches. Ro, remember, was 6 inches. Alright, and we solve all this out, you get sigma theta would be equal to sigma theta would be equal to 6,000 psi. Alright, so significantly larger. Alright, so if we plug in 6,000 psi into our equation for u of r, alright, what we end up getting, we plug in r and we plug in e, our u of r is going to be equal to 2 times 10 to the minus 4 inches. Alright, and then we know that u of r is equal to the change in our radius of our inner radius of our disk at 5,000 RPM minus the inner radius at 0 RPM. Alright, so our inner radius at 5,000 RPM is going to be equal to 1.00 inches plus our change in radius 2 times 10 to the minus 4th, which is going to be equal to 1.0002 inches. Okay, so alright, so using these two values that we had just solved for, alright, we can then solve for our interference delta. Alright, so our interference delta is going to be equal to the outer radius of our shaft minus the inner radius of our disk, alright, which would be equal to 1.003 inches minus 1.0002 inches, which would give us about 0.0028 inches. Alright, so once we have our delta, we can plug it in to this equation here, and we can get our pressure P. Alright, so if you plug in, so for all these terms here, we had just solved for delta. We have our elastic modulus and our Poisson's ratios. So EO is equal to EI, and that's equal to 30 mpsi. Our Poisson ratio for the inner and the outer is all going to be equal to 0.29, and then our for the rest of our terms, B, we're going to plug in B is going to be equal to 1.0 inches. All right, it's close enough for both of them. And then our inner radius of our shaft is going to be equal to 0 since it's a solid shaft. And then our C is going to be equal to the outer radius of our disk, which would be equal to 6 inches. Okay, so alright, and then this part here, this B here, is going to be our radius of our is also going to be, it's the same B, to be 1.0 inches. Okay, so plug in all these terms in. what we end up getting for our pressure is we're going to end up getting 40, 30, 80 psi. Okay. All right. So once we know our P, we can then determine sigma R pressure, sigma R rotation, sigma R sigma theta pressure, and sigma theta rotation, and combine to get our total stress, sigma R and sigma theta total. Okay. So, all right. So what we end up getting, all right, is for the disk. All right. So if we're looking for the disk only, all right, we can find for the stresses due to the pressure. We can say we have sigma R and we have sigma theta that are due to the pressure. All right. Now we can use, these are going to be equations 12 and equation 13. All right. So these two equations, which we had earlier in the lecture, what we'd end up getting if we plugged in all the constants that we had. So we basically have these are functions of the inner radius, the outer radius, and the internal pressure of our disk. All right, the outer pressure in this case is 0. All right, we plug in all those values. What we end up getting for sigma R pressures, we get 1166 psi minus 42,000 pounds divided by the radius squared, and then for the tangential stress, it's again 1166 psi plus 42,000 pounds divided by the radius squared. All right, and then you can repeat the process for the stress due to the rotational velocity. All right, so if we solve for sigma R due to rotational velocity, we can do the same thing for sigma theta due to rotational velocity. All right, we plug in everything here. This is equations 29 and equation 30. All right, what we end up getting is we get 3066 psi minus 229.83 pounds per the radius squared minus 82.9 pounds divided by the inches to the fourth times the radius squared. All right, and then the tangential stress would just be equal to 3066 psi plus 29.83 pounds divided by the radius squared plus or minus 47.1 pounds divided by the inches to the fourth times the radius squared. Okay. All right. So again, just use equations 29 and equations 30, plug the values in, and you'll get these numbers. And then the last thing here is we'll have the radial stresses, the total radial stress and the total tangential stress would just be to sum up these equations, sum up these values together. Okay, so the total radial stress would just be equal to 1166 psi plus 3066 psi minus 42,000 pounds minus 29.83 pounds divided by r squared minus 82.9 pounds inches to the fourth r squared, and then we would just add up the tangential stresses due to pressure and omega to get our total tangential stress, and that would just be equal to 1166 psi plus 3066 psi minus I should say plus 42,000 pounds plus 2983 pounds divided by r squared, and then we would have minus 47.1 pounds divided by inches to the fourth times r squared. All right, and these would be our total stress distributions in the disk due to the interference pressure and the rotational stress.